Hi all. In this lesson, we're going to do a hands-on demonstration of fitting metalogs to data. We're going to do this in Excel. The goal by the end of this lesson is for you to be able to put in your own data sets and quickly, within 30 seconds or a minute or even less, be able to fit your own data set and find a good metalog that will represent your own data set. Also, at the end of the lesson, we'll talk to some degree about how to automate this process and how to prepare the workbook to just drop in your own data. This workbook here is the same as the ELD Metalogs workbook. And if you did not, if you haven't looked at that previous video, you might want to do that before proceeding with this lesson. Here we have a modified version of the ELD Metalogs workbook, which is called the ELD Multi workbook, and it means multi-data set. And again, that is downloadable like the others from the metalog.org website. The difference is that the ELD Metalogs workbook works with only one data set at a time. As you can see down here, the multi ELD Metalogs workbook allows you to put in multiple data sets, in this case, up to 10. And so when you download that spreadsheet from metalogs.org, you'll see 4 blank data sets, and you'll see 6 illustrative example data sets, which I'm going to work through in order to show how one works through the data fitting process. The first data set, as you can see, is just 10 points from a standard normal distribution. That's the data set that's being accessed by this data set number 1 index up here in cell C10. And you can see that 10 points from the standard normal CDF makes a nice smooth shape that a metalog fits very easily. And of course, here's the metalog panel for how it looks for various numbers of terms. Almost no difference after you get up to about 4 or 5 terms. Second data set is going to be 100 samples from a normal distribution. This includes randomness, and so the data will not be so smooth. Third example will be the fish biology example from my 2016 paper. Here's the reference, section 6.1.1 of the steelhead weights. The hydrology gauge height for the Williamson River, also from my paper. The bidding decision analysis from section 2.2.2, that data set is here. And then finally, a data set submitted by a student that is interesting for various reasons I'll explain, having to do with the bill length of Arctic or Antarctic penguins. So let's go ahead and get started. First, the functionality, as I mentioned, of this workbook is the same as the ELD Metalogs workbook. And so all of this, these intermediate calculations on the right are just the calculations the spreadsheet is using to calculate the graphics and the other information here on the left-hand side. So you can move those out of the way. For example, you can insert columns, and all those calculations are still there. They're just moved off to the right, so you got plenty of room for other things on your spreadsheet. And at this point now, we will focus in on just the centerpiece, the left-hand side of the spreadsheet, and then we'll begin to get going here. So let's take a look at the first data set. As I mentioned, 10 CDF points from a standard normal distribution. This one's easy. Those data points are very smooth. Metalogs will just basically immediately mold themselves to the shape of this kind of data. And if I look at the number of terms here, I've got a 5-term metalog in the large 2 graphics in the center here. If I go to 6, 7, 8, 9, 10, you see virtually no difference in any of these shapes, and that's because a 5-term metalog captures this particular shape very, very well. Let's move on to the second data set. I would do that by going up here and using this little control here to go to the second data set. This one is 100 samples from a standard normal distribution. Now, as you can see here, 5-term metalog does a very good job of capturing this, the shape of this sample. But as you can see, the sample's not nearly as smooth because it is a random sample of 100 data points. If you go up in the number of terms from here, 6 term, 7 term, 8 term, 9, all of a sudden you get something that's pretty squiggly. That does not look very much like a normal distribution. However, the Metalog is fitting the data more closely with a 9 term, and with a 10 term, it's even more close. And if I go to 11, 12, 13, then it's really, an odd shape. There's 12. Look at all those false peaks are basically overfitting. And the Metalog panel with all the little thumbnail PDFs on the right gives you a way to instantly see how much difference it's making, how much difference adding additional terms makes. In this case, you could use 4, 5, 6, anything like that, and that would give you a very good representation of this data. At this point, I would like to introduce the idea of regularization. This is a good example to do it. Regularization adds a small constant to the matrix that gets inverted as part of the least squares to the diagonal elements, and that causes the A coefficients. As you can see here, the A coefficients get very large as you go up to 12 terms. Well, if you start adding regularization, you'll see these things. First of all, it makes some feasible that were otherwise infeasible in the Metalog panel, but also they get smoother. You see, if I add more regularization, it just smooths it out. I don't actually use regularization very much, but it is a feature of this worksheet that you can use if you want. If you don't want to use it, just go ahead and set it to 0. Let's go on to the third data set. This is the fish weight of 3,474 steelhead from the Babine River in British Columbia that were caught in the years caught and released in the years 2010 through 2014. This is the one that in my paper I showed has a bimodal shape, and we explained the reason for that is that the fish in the river consists of 2 populations, 1 salt and 2 salt fish. That is, it's the first time back up the river to spawn, or their second time back up the river to spawn, which are basically these 2 peaks here. But this is if you model it. Now I've got a 12-term Metalog in here. I think in the paper I probably used a 10, so we'll go down to 10. It's almost exactly the same shape. It becomes very, very stable. However, if you did what most people would have done, which is to model this with something that looks like a log-normal distribution, that would be similar to maybe a 4-term Metalog, you would lose the nature of the 2 peaks. Now, for some data sets, you might say, well, this is a bimodal data set anyway, so I'm going to use a 4-term Metalog. Or maybe a 5. There's also a unimodal data set in this case. But if you have contextual background that suggests that there's a significant insight there having to do with the empirical data, you might have a reason for wanting to use 9 or 10 terms. And this is, as I explained in the 2016 paper. Let's take a look now at the next example, data set number 4, which is the gauge height of the Williamson River. This data came from the U.S. Geological Survey. Williamson River is here in Oregon, and that was for the years 1920 through 2014. There are 95 points. You can see up here the sheet counts however many points you put in the data set, and you can put any number of points of data in here. It says here anything between 2 and 10,000 data. This is dimension to go down for 10,000 if you want to do that. In any case, in terms of the Williamson River, once again, you might have thought, well, this is a very good fit at 5 terms right here. But as you increase the number of terms, 6, 7, 8, 9, 10, you quickly see that there's a shape here, which, as I explained in a previous video in this course, may very well be indicative of the shape of the bottom of the river. And this is something that a hydrologist said to me when I presented this one time in a class, and he explained how. And I've already covered that in a previous video here. So once again, that's a very simple data set to capture. Let's take a look at the bidding simulation. That's from section 6.2 of the paper, and that's data set number 5. And once again here, anything between, oh gosh, 5 and 10 terms looks almost exactly the same. Finally, when you get up to 16 terms, this is wavy. And what I believe about I believe this is a smooth simulation, and I believe it's a unimodal data set. I have no reason to believe it's trimodal, as you see in this n equals 16. I think this is just an example of overfitting the data. But once again, by simply looking at this metalog panel, you can sort of quickly focus in on how many terms you might want to use. In this current case, I probably would use 5 terms. But these small number of terms are not always appropriate, as illustrated in this example number 6, which was submitted to us by a student that took one of my courses last year. And this is a study. You can look it up in the literature. Everything, including the DOI number, is in the reference here. But it's from ecology, and this is a data set of 342 measured bill lengths of Antarctic penguins. And when we first fit this data set well, you just plug in the data set and then you look at the metalog panel. Look, with 4 or 5, you've got a unimodal distribution. With 6 through 10, it's bimodal, and with 12 and 14, it's trimodal terms. And you say, well, how can that be? And I suggested to the class that unless there is a reason for the distribution to be bimodal, that lacking any other information, and I haven't read the study myself, but lacking any other information, I'd probably pick a 4 or 5 term metalog. Here's what the 4 term metalog looks like. And that, as you can see, the line of the 4 term metalog goes very nicely through this data. The student at that point said something very interesting. He said, well, there's something I didn't tell you, Tom. In fact, I was just putting this in there to test the metalogs, but he said this data set actually consists of 3 different species of penguins. And so he said, I might tend to, if I were picking the best distribution to represent this data set, I might pick the 12 term, for example. So the bottom line here is that picking the best of the metalog distributions for a given data set is something that typically requires some judgment, or it can require some judgment and some contextual knowledge if you're fortunate enough to have that. Now, I'd like to mention a couple of other things here. If you wanted any of these data sets to have different bounds, here's where you set the bounds. This one is set for an unbounded data set, but if I wanted it to be a semi-bounded data set with a lower bound of 0, I could simply change that. And now you see that it has all the same data points, but you have a distribution that has a lower bound of 0. If you wanted to have a bounded data set, you could do that for any of these curves. Let's just say, oops, it didn't. Let's see, go to the bounded one here, and the bound could be, let's say it's 100, just for example. And now we've got we have a distribution, a representation of that data that has an upper bound of 100 and a lower bound of 0. If you wanted to override the bounds you put in the data set just temporarily, see what would happen if I make the lower bound, let's say 80 instead of 100, I could say the upper bound override here is 80, and I could put that in. And now my graph and all the parameters over here would reflect a data set with a bounded data set with an upper bound of 80. You can do the same thing for overriding the lower bound if you like. I've got it set down here to be a bounded distribution, but if I wanted it to be an unbounded distribution, I could use this override here, and it would go back to being an unbounded distribution. So that's the quick introduction to data fitting with metalogs. Now, some of you may be saying, gee, I have a lot of data sets and I don't want to have to manually intervene in order to figure out what's the best metalog for my data set? And maybe you have hundreds or thousands of data sets of financial assets or something else that you'd like to have a good metalog representation of without having to go through the procedure of looking at each distribution as we've done in these examples. And there are some ways to automate this. One, for example, might be to just simply decide that you're going to use, let's say, a 5-term metalog, because a 5-term metalog is something that will almost always give you a pretty good representation. Take a look at this one here for the bill lengths. Let's go back a data set. Let's go to data set number 5. Boy, 5 terms is a real good match to that data. Let's look at data set number 4. That's a very, very good match. Again, for the gauge height, if I go to data set 3, it's still a very good fit, 5 terms, but it misses the contextual knowledge of the 1 salt versus 2 salt fish. Data set 2, it's a very good fit. Data set 1, it's nearly identical. So you could go with a decision rule, like always use a 5-term metalog or a 4-term metalog, depending on how much detail and shape you wanted. Another possibility is to use something like a 9-term metalog, which would give you the opportunity to observe, for example, bimodal shapes. So if you went with a bimodal, a 9-term metalog, then we'll go up in the data sets. We'll go to data set 2, very good fit, interesting, probably overfit, but good. 3, 4, 5, 6. So the 9-term does very well also. In the case of the penguin bill lengths, it would have missed the trimodality or the potential trimodality. But nevertheless, and then it's also possible if you went with something like a 9-term metalog, it might be infeasible. So then you could adapt your automated rule to say, I'll go with the highest number of terms that is feasible with a maximum of 9 or something like that. And depending on your particular the context of your application, you can probably come up with a rule that will help you do this fitting in an automated way. So lastly, getting to the goal of all this, as I mentioned, I wanted you, or I do want you, to be able to fill in your own data sets and play around with them. And in order to do that, you can simply delete all of these data that are here. And now you've got a blank workbook, and you're free to fill in your own data sets and learn what you can about them and fit them to metalogs and quickly pick what would be the best metalog for your various data sets.